Alright, welcome to the Problem Solving in Algebra and Geometry lecture video for pages 9 and 10. This video should cover all of the algebra tools that you're going to need to be successful on pages 9 and 10, so make sure you take some good notes. So we're revisiting Chris Johnson, who's the fastest player in the NFL. He runs a 40-yard dash in 4.24 seconds. And we want to know if he catches the ball 7 yards deep in the end zone, how can we write an equation that states his distance from the goal line in yards, t seconds after he catches the ball. I then want you to use your answer to determine how long it will take him to score a touchdown. So I think the first thing we need to realize is that we need to convert 40 yards in 4.24 seconds into yards per 1 second. So we can realize that 40 yards in 4.24 seconds is the same thing as simply dividing 40 by 4.24 to give us yards per 1 second. So we can put this guy into our calculator, and it will give us a nice number of 9.433, and again this is in yards per 1 second. And it might be a good idea to save this number in your calculator for rounding purposes later on, because we always want to round our number at the very end of the problem. So now we need to figure out how time affects his distance from the goal line. So I think if we just draw a nice two-dimensional graph, we can realize that since he starts 7 yards deep in the end zone, it's almost like he's starting at -7. Because if he starts at the 0-yard line or at the goal line, we can think of that as starting at the x-axis, at the origin 0, 0. But he's 7 yards deep. And we can think of 9.43 yards per second as a rate of change or a slope. So I think if we think of a graph, we'll have a y-intercept of 0, -7, and our slope is going to be 9.433 yards per second. So if we label our axes, we're going to realize that we have time in seconds, and we have distance, our y value, in yards. Alright, so now we have a y-intercept and a slope, which makes it, I think, pretty easy to write the equation of a line. So I think we can write our line as y equals 9.433x minus 7. And our y, again, is going to be our distance in yards. And our x value is going to be our time in seconds. So I think this pretty clearly writes the equation as a distance from the goal line, again realizing that we're starting 7 yards deep in the end zone, so writing that equation in terms of t seconds. So the second part of the question asks us to determine how long it will take Chris Johnson to score a touchdown. So I think you need to realize that in order to score a touchdown, our distance, which is y, has to be 100, because a football field is 100 yards long. So our distance is 100, so 100 equals 9.433x. And again, x is our time in seconds, which we are searching for, minus 7. So I think we all know our first step here should be to add 7 to both sides, which gives us 107 equals 9.433x. And to isolate x, we'll simply divide both sides of the equation by 9.433. And we should plug this into our calculator, again, saving the full 40 divided by 4.24, that full answer in our calculator without rounding it. So we should enter 107 divided by 9.433962264, and we should get a nice answer of 11.342. And again, we're searching for x, which is time in seconds. So it takes Chris Johnson 11.342 seconds to run 107 yards.
Sadly, Mr. Mastercola had to run off to dorm duty, so you're stuck with me finishing up pages 9 and 10. Two other topics you might need for handling pages 9 and 10. The first is just a little review on how do you graph on a number line. You probably did this at some point last year. We'll just do a couple of examples. One would be all numbers greater than 2. So if I wanted to represent on a number line all of the numbers greater than 2, the first thing you need to notice is that it says greater than 2 and not greater than or equal to 2. When it's greater than 2, that means we put a circle here. The circle at 2 means that 2 is not included. But then I want things greater, which are things to the right, which means you darken in the number line to the right of 2. So this represents all of the numbers that are greater than 2. If, again I don't here, but if I wanted to also say all the numbers greater than or equal to 2, then this just becomes a filled in circle, which tells us that 2 is included plus all of the numbers to the right. But again, for this problem, we only want what is in red, which is a red circle, and shading everything to the right. All numbers less than or equal to 4, well, now it equals 4, so I'll put a dot at 4, and everything less than is obviously the numbers to the left of 4. 2 is less than 4, 0 is less than 4, negative 2 is less than 4, negative pi is less than 4. Any numbers to the left of 4 should be shaded in. Another possibility could be all of the numbers between negative 2 and 4. Well, on this guy, everything between negative 2 and 4 should include, is going to include the numbers between 2 and 4. Now it looks a little better. I want to show the numbers between negative 2 and 4. Since this doesn't seem to include negative 2 or 4, I will put a circle at negative 2. I will put a circle at 4, including all the numbers in between. I would just shade in those regions. Algebraically, we could also show these. If x represents my number, the way we would show all numbers between negative 2 and 4, I put a negative 2 on the left, a 4 over here, and then less than symbols for both, because remember, think about the alligator idea. This is the alligator, negative 2 is, I don't remember the alligator idea, but x is greater than negative 2, and x is less than 4. That's what this means algebraically. So all numbers between negative 2 and 4 is represented on the number line like this, represented algebraically by x being between negative 2 and 4. And you can see this means x is greater than negative 2 and x is less than 4, which gives us that spot on the number line. Obviously all numbers less than or equal to 4, you just write x is less than or equal to 4. And for the top one, x is greater than 2. You can figure that out as well. So just a quick little review of the number line graph. Final thing we want to talk about for page 10 is just a quick little review of adding fractions. Look at the one on the top. I've got 1/4 plus 2/4. This one I can add pretty easily. So remember, a fraction just represents a portion of a whole. So 1/4, the idea could be, we have a pizza that we broke into 4 pieces, and 1/4 of that is one of those 4 pieces. 2/4 would be 2 of those 4 pieces. I'm adding those together to figure out how much of the pizza is represented. And obviously 1/4 plus 2/4 is 3/4. When you add the fraction, if the denominator, remember the bottom part is the denominator, and the top is the numerator. If the denominator is the same, you can simply add the numerators together, keeping the denominator the same. Right? Think about what that means in terms of the pizza. You don't want to add both of them, right? 3/8, that's not going to work. If you have the numerator and the denominator, that's like saying, I ate 1/4 of the pizza, you ate 2/4 of the pizza, and all together we ate 3/8 of the pizza. I don't think so, because you ate half of it yourself. So there's no way that together we ate less than half of the pizza. So just remember what the fractions mean, and you should be okay. The second example down here, 1/3 and 3/5, it's a little trickier. The denominator is different. It's analogous. If you look at my little, little drawing down here at the bottom, my little picture, I've got a dime and a quarter. I can't add 1 dime and 1/4 and say that I have 2 dimes or 2 quarters. I have something totally different. I can add 1 dime and 1 dime and get 2 dimes. That would be fine. Well, if you think about what these represent, a dime is 1/10 of a dollar. So if I wanted to, I could add 2 dimes, meaning 1/10 plus 1/10. 1/10 of a dollar plus 1/10 of a dollar should be 2/10 of a dollar, aka 2 dimes or 20 cents. Well, if I want to add a dime and a quarter, obviously a dime is 1/10 of a dollar, and a quarter is 1/4. Hence the reason we call a quarter a quarter. 1/4 is also known as a quarter of a dollar. If I want to add a dime and a quarter, I'm in trouble. Now we all know that a dime is 10 cents and a quarter is 25 cents. Add those together, we get 35 cents. Remember, 35 cents, 35 per 100, right? That's 35 hundredths of a dollar. Well, we should be able to get the same thing by adding these fractions, but I'm going to need a common denominator so that I can add them together. Obviously, 10 is not a multiple of 4, so what I need to do is turn both of these numbers into something that has the same denominator. There's technically an infinite number of ways that we could do this. The lowest is probably to turn them both into something over 20. So if I want to turn 1/10 into something over 20, I'm going to multiply the top and bottom by 2. Remember, this is very similar to the unit conversions that we did a while ago. If I multiply the top and bottom of 1/10 by 2, 2 is just another way of writing 1. 1/10 times 1 is still going to be equal to 1/10, but now I'm writing it in the form 2 over 20. 1 dime is also 2/20ths of a dollar. To get the 1/4, obviously I need to multiply 4 by 5 to get 20. So I'm multiplying the top and bottom by 5, aka 1, and I'll get 5/20ths. 1 dime is 2/20ths of a dollar. 1/4 is 5/20ths of a dollar. If I add those together, since now I'm talking about both being 20ths of a dollar, so 2/20ths of a dollar and 5/20ths of a dollar should give me 7/20ths of a dollar, aka multiply both by 5 if you wanted to, and I'll get 35 over 100, or 35 cents. You should be able to do this one for a little practice on your own. Multiply 1/3 and 3/5. Probably turn both into 15ths, and then you should be in great shape for page 10. Have a great time. See you tomorrow.